under the right conditions, polymers flow like fluids. The simplest description of fluid flow is the Newtonian flow of liquids. So if we look at the figure here, we have a setup which there's some shear force applied to some volume of material. So there's a force applied moving at a rate v, and this sets up a velocity gradient in the material described by the velocity divided by the thickness that the shear is across. This velocity gradient gives rise to what's known as a strain rate within the material, which is described by essentially the change in the rate of the x direction divided by y, which is often described in terms of the rate of change of the angle theta dot there, and theta on this figure corresponds to this angle here. So the rate at which the angle changes, the dot above it to make it a time derivative, gives you the strain rate. By analysing this sort of flow, you can find that it follows what's known as, for simple liquids, it follows Newton's law of viscosity, which has the form shown here. So we have some stress is equal to the shear strain rate, so this the V over Y, multiplied by some constant factor which is known as the viscosity of the material. We generally use the symbol eta for that. So that's Newtonian flow. Flow in polymer systems is generally a bit more complicated than Newtonian flow. The reason for this is that the polymers are entangled with each other, so they move over each other in a rather complicated way. So if you remember the discussion about the reptation motion that they have to go through in order to move through the entanglement. And there's also effects known as entropic effects. Now this is related to the state of disorder within the material, and we'll visit this again later on. And the combination of these things means that the polymer fluids effectively have, it's like a memory of the position they used to be in. So when the shear forces on them stop, then there's a tendency for the materials to move back to the position that they were in before the deformation was applied. Overall, all these effects mean that the flow properties are a bit different to that seen in Newtonian fluids, and this description of the flow is most often done through what's known as the power law description. So we have a relationship of this form. We have the shear stress set up within the material is again proportional to the strain rate in the material, but the strain rate is now raised to some power, n, and the viscosity term is replaced by something that's known as the consistency index. Now that the exponent term n gives a variety of different behaviours depending on the value of n. When n is equal to 1, we get back to the Newtonian fluid description. When n is less than 1, we get an effect known as shear thinning. So as the strain rate increases, the stress actually decreases within the system, and this is what's seen for most polymer systems. For values of n greater than 1, we get a situation known as shear thickening. In shear thickening cases, you increase the strain rate, the material actually, the stress gets higher, and you get strange effects where if you apply high strain rate to a shear thickening liquid, it'll actually turn into a solid. A reasonably familiar example of this is sort of tomato ketchup type sauces, which if you squeeze them gently out of the bottle, they will flow slowly, but if you try and force them out quickly, say by hitting the bottle on its end, try and get into the food, the material actually turns into a solid, and then it will actually fracture like a solid and come flying out of the bottle if you hit it too hard. Now I'm going to look briefly at elasticity in materials. Now in most solids, the elastic properties arise from the interatomic forces that make up the solid, and we get, for a very wide range of materials, we get this sort of potential energy curve. When you look at the effect of the separation of the atoms in a crystalline solid, you see that there's a point at which the potential energy of the system is a minimum, and that corresponds to the unstrained value of the atomic separation. And if you move the separation away from that value, either decrease the separation, which corresponds to compressing the material, or increase the separation, so stretching the material, you move up the potential energy curve. The reason that's important is that there's a force arises from that movement that's proportional to the way in which the potential energy changes with respect to the atomic separation in this way. So we get, whether you compress a material or extend a material, you get this force arising from the separation of the atoms that gives rise to elastic effects. And from this sort of effect you can show that you get things like the familiar Hooke's law and factors like that. Now, that's for solid materials, but polymer melts display a very different sort of elasticity, and we're going to look at that next. To understand how polymer melts behave in an elastic manner, we're going to look at a model that was originally developed to describe the way rubbers display elastic behaviour. So it's a model of rubber elasticity, and it's something that depends on the entropy of a particular material. Now, entropy is a measure of how disordered or random a system is, and it's also can be described as a measure of the amount of energy which is unavailable to do work. It has to be dissipated as heat. Now, one of the things that you can show from thermodynamics is that an isolated system will move towards a state with higher entropy, so things would always want the higher entropy. One of the great workers in the field of thermodynamics was Boltzmann, and he showed that the entropy of a system can be described as being proportional to some constant times log of the number of arrangements of energy within a system. So if we remember that definition for the next part, all will become clear, hopefully. Another key thing that comes out of thermodynamics is the concept of free energy. This is the amount of energy available for a system to change its state in some way. It's a bit like an object high above the planet will fall down, losing gravitational potential energy. So in that case, the free energy arises from the potential energy. Now, for lots of systems, the free energy can be described as being given by the difference between the internal energy of the system, so that's the stuff bound up in bonds and things, so that's not available to do work, minus a factor which is given by the temperature times the entropy of the system. Now, given that, so looking at that, what we have to remember is that a system will always try to minimise its free energy, and the best way it can minimise its free energy is to, at a given temperature, is to maximise its entropy. And in order to maximise its entropy, what it's got to do is access lots of arrangements. Now, when a cross-link system like a rubber or a polymer melt, which is an entangled system of chains, is deformed or stretched in some way, you actually get a reduction in the entropy. Because what's happening there is you move from some highly disordered system, which for a polymer melt, for an isolated chain, corresponds to a ball of random bond arrangements. When you stretch it, you actually start to align the polymer chains in one particular direction. So that's improving the amount of order, so that's reducing the entropy. So if the entropy is reducing, the free energy of the system must be increasing. Now remember, systems want to reduce their free energy, so the effect of that is that nature gives rise to a force that resists that increase in free energy. And so it resists the increase in free energy, and whenever possible goes back to the original state it was in, going back to a reduced free energy. So the change in entropy actually gives rise to an elastic effect, and we call that entropic elasticity. And that's the reason rubber is stretchy and goes back to its shape. And actually in polymer melts, due to the entanglements, polymer melts also have distinctly elastic properties. All these effects mean that polymer samples can be elastic, and they can have viscosity effects, and they can have a strange mixture of the two, particularly when you have the entropic elasticity effects as operating as well. So and just what goes on in a material depends on the temperature you're looking at and the time scale over which you're working. We'll look at how these things depend on each other in a later lecture, but just for now remember that we can have elastic materials which just depend on the separation of the atoms in the system, and at one end of the thing, so these are polymers in this state tend to be just as hard as most materials are, and at the other end we get liquid materials, but with funny or rather odd flow properties. We have this strange power law dependence because of the entanglements, and there's a range of properties somewhere in between all these factors.